Thank you, Doug. Good morning, everybody. It's interesting listening to Ian and Peter talk about EME and kind of a little bit of the divide and where we've been and all that. And I must admit, I heard my first echoes on 2 meters back in 1974. I had 4 Swan antennas and a pair of 4 CX250Bs. And I could see the moon coming up over Richardson, Texas, and it was the most fun thing in my life. I mean, I even called up my friend at work who was not a ham, and I had to, tell him how happy I was about it. And that's really a big thrill. And that was building a MS-175TE, which I think was a TIX 105 newer version or something. And, I worked at TI, so it was kind of neat to get the devices and build up the preamps. And, of course, I've been doing that for years, and that's really the fun of it. But, for me, the real excitement was going up in frequency. So I just kind of worked my way up in frequency and went back down a little bit to work some of the odd bands that not all of you have, like 222 and 902, and then kind of work forward a little bit more. And I even went down to 6 meters when I got a little disgusted with 47 gigahertz and kind of moved forward again. So for me, the excitement was doing it with, going up higher in frequency and the technology. And the biggest hurdle back then, and still is today, is LNA stability, even stuff I build, okay? But I remember my W1JR cavity input preamp using an FJ203 that Russ Wicker came up with, and nice little preamp, and we didn't quite understand stability too much there, but you had noise figure at 432, and you had a lot of gain at 384 megahertz, it seemed like, so you had to put a cavity filter in front of it. And they weren't too happy with one another, and if my wife was here, she'd kind of support the fact that I about threw in the towel more than once. I mean, it was a tough go, and I did miss HK1TL when they came on down in South America. So, it's been a little bit of a rough time, but I got to tell you, it's the most fascinating part of ham radio I've been into. And what I want to talk to you about right now, is a little bit of 24 gigahertz, which is seeing additional activity. In fact, all the microwave bands are probably seeing more microwave activity on all the bands now than we've ever had in the past. So even with all the 2-meter digital going on, which is, that's really, what you have to do to get on 2 meters these days. That's just the way it is. But on the upper bands, there's just so much more activity, and we have to thank Peter to a great degree for that, for having these activity weekends that we've been having for the last couple of years, and it's really helped a lot of activity. And it's probably at its peak right now. And, you've got most of the equipment out there you need to get on those bands. So it's a fun time. So I'll talk a little bit about the history of 24 gigahertz, the early activity, kind of where we are now, a little bit about equipment and some of the challenges. And if I have a little bit extra time, I'm going to jump past the conclusion slide and go into a couple other pictures and then kind of revert back. So I'll kind of stumble through that at the end. But maybe I have some time to show you some other pictures that might be of interest to you. So the first EME QSO was made by Barry and myself on August 18th, 2001, which I think is about 10 years after the first 10 gig EME QSO happened between Jim Vogler and Kent Britton. And, it took years of work to make preamps that work, because I designed my own preamps. I didn't buy a DB6NT until about 5 years ago, but I did. But man, I had to build my own, and I was using the old Avantech devices, HP Agilent devices, and it turns out my latest LNA prior to buying a DB6NT actually used an NEC device, but I didn't tell my boss that at the time. But anyway, that was years of hard work with feeds and the dishes and all that, but the biggest missing link was the TWT. And Paul Drexler, W2PED, had a small supply of 100-watt tubes and power supplies. And so Barry and I were lucky enough to get a hold of those. And we did have to do some modifications and to finally get it going. But we both had about 100 watts early on. So we made the QSO and run some tests for a few years. And we could hear the other station with as low as 10 watts, even though the nominal power was 100 watts. But we ran tests and then waited for other people to come along. And guys that like Sergey RW3BP, a couple other guys in North America, OK1UWA, Willie, G4NNS, DK7LJ, and you can see the list. These are some of the guys that were on in 2008 or so. And more recently, there's been even more interest. Smaller stations getting on, which provide more of a challenge. But F2CT, OZ1FF, RK3WWF. These three guys have made QSOs with the bigger stations like OK1KIR and LX1DB. IK2RTI is a new on the block and looking to make some Qs. And I'm not sure if Andre yet has made a Q. He was operational or looking to be, or he is operational but looking to make a Q in just recent times. So he may be added to the list as well. And then most notably, the first Japanese station came on the air, JA6CZD, and he worked OK1KIR recently. So we've got several continents on right now, and maybe we can talk Bruce, PY2BS, to get on from down under, or even Doug, 24 gigahertz, right? So anyway, the band in the U.S. Is from 24,000 to 24,250 megahertz, and most of the activity was on 24,192 originally because that was the tropo frequency, if you will, in the U.S. and in Canada. So when Barry and I first got on, we were on 24,192, and guys like Willie and some of the Europeans were also on 24,192, but we had since decided to migrate to 24,048, kind of like what we've done on in the 9-centimeter band. We've migrated to 3,400, which kind of alienates some of the terrestrial guys in some of the areas, but just trying to get rid of the problem we have on 13 centimeters, which is everybody operating in different parts of the band due to local limitations. So we pretty much decided on 24,048, and that's where we're kind of sitting at the moment. So what does it take to get on? Well, this is my first dish. This is a 3-meter Andrew dish that a fellow from Andrew Corporation, his wife told him to get it out of the backyard, so it went into my backyard and got it running. But one of the biggest problems I had was I don't think the dish was exactly planar, if you will. Now, I must admit I didn't set it down on a flat surface to make sure it was totally quite planar, but I built it and realized I needed some performance improvements, so I added this back structure right here. And using the old string trick in front and to see if the two strings will overlap, from one at the top and the bottom and one from the left and right. And if they overlap, then, and if you can rotate the string around a little bit, you can see if the dish is totally planar or not. Well, mine apparently wasn't. When I added the back structure, it helped considerably on sun noise and moon noise, and that's what all this is for right here. And that did help considerably. And this was a little Scientific Atlanta positioner. That was kind of wimpy, but it was all I had at the time. But that's what we used to make the first EME contact. And a 3-meter dish is a nice sized dish. Willie LX1DB, I'll show you a picture of his later. He has a real nice dish and does very well. And OK1KIR group has a 4.5 meter dish under illuminated, and it works very well. But then you'll also see pictures of some small offset fed dishes. So you don't necessarily need anything bigger than this. Get it right here. And this is Barry's. This is a 2.4 meter offset fed dish. And of course, with the offset fed dish, the advantage of this is you can put all your apparatus here, and with the offset geometry, most of this is out of the field of view of the beam of the antenna. This was the dish that I put up recently. Actually, this was a 2.4 meter dish that I used on 47 gigahertz EME. And after we were done with that, and I had moved some things in the backyard, I decided to go to this particular dish. And here you can see, here's the feed system here. Here's the 100-watt TWT right here. It's a little bit shadowy, I think. And here's the transverter. And actually, this is something I added recently because I did the string test on this dish, and I noticed I was out a half an inch. Well, half an inch is really a wavelength at 24 gigahertz, so it's actually a lot. So I tried replumbing the dish, if you will, and this is like brute forcing, a fiberglass dish, not the easiest thing in the world, but actually did make some slight improvement with this. So work continues, and we'll see what breaks in the stressing process, if you will. And this is on the back side of it. This is just a standard Azel rotor from a satellite installation. This was a VSAT installation up in northern Minnesota, up on 14 gigs and down on 12. So the dish was not rated to 24, but it seemed to do really well. I'm using just actuators for the elevation and the azimuth. This one actually cratered out on me. The thing stripped out. I heard a big thunk in the backyard, and the whole dish fell down, and The TWT still works. I think I'm down a few tenths of a dB. Maybe I shook something or whatever, but I decided to go out to, I think it was Dawn Satellite Corporation. This is a big, what I call whammy-jammy actuator that has like a limited slip clutch in there. So if it decides it can't move, it won't strip itself out. It'll just stall out. So I was happy to do that. Now these are, I'm actually using absolute encoders right here for this one here is for azimuth, and there's one over on the side box which you can't see here, which is for elevation. So it's like an inclinometer, and use Cat5 cable to bring it back to the shack. And it's US digital, so there's a Cat5 to I guess an SEI adapter, which takes it down to either RS-232 or USB, and that's how I get my my readout. Here's a picture of the LNA box. Down in Texas, we need something that is hail-proof. So I got this big box from Home Depot, which is our home improvement place. And you can see a little something hanging out here. This is a little cooler for the LNA, and I'll show you an inside shot of that. And most recently, I've been playing around with flares. This is something, it's a brass feed, but it's also, I used a piece of aluminum ducting for the prototype. So this is just a start, and I know I got dissimilar metals here, so this is not going to be a long-term solution. But the flare actually does help on sun noise, and we all use sun noise as the final, or sun noise and moon noise as the final indicators as to how well our systems are performing. This is an inside view of it. Here's a WR42 waveguide switch. Here's my feed, and here's the flare, and here's the DB6NT LNA. And I have a small Peltier cooler with a heat exchanger, if you will, with a couple of fans here. And this will drop it about 25 F, which is from about, like this summer, it was like 105 F. So that's like a little over 40 C down to about 75 F, which is what, in the high 20s or maybe 30 or something. So it'll drop it significantly. And the reason I did that, or drop the noise figure, is I got this graph from Johannes, DF10I, that shows what he did to actually cool the LNA and the effect that it had. Now, I got to make sure I don't run it below dew point here, because it does actually, you can tell it's kind of raining on the outside of the preamp, and don't know what's going on the inside yet, but I tried to keep it just shy of dew point. And of course, it's so hot in Texas, our dew points are like 75 F, and so I could just barely get down to 75 F when it's 105 out, but that's, significant. But you can see the improvement here, even from, say, 40 C down to 25, so very hot to room temperature. There's a couple tenths of a dB decrease in noise figure, and this is really significant because actually, you can see several tenths of a dB improvement in sun noise and maybe a tenth in moon noise. But it tells you that since we don't have a half a dB noise figure preamps here typically, that cooling it can help. And of course, the next step would be to evacuate the housing to lower the dew point inside the housing so it doesn't precipitate, and condensate and get on the circuitry. So that prompted me to try what I did in the other picture, and actually saw a significant improvement. And if I can see a tenth of a dB improvement in moon noise out of maybe a tenth or two out of 1.5 or 2 dB, at least it's an improvement. I mean, we're trying to go for every tenth that we can go for. All right, so this is my experimenting with feeds, and I'm not a machinist, so I'm going to take the easy way out. We get hobby brass at the hobby store and such, so that's what I built up here. And this one here, I was trying to think back of the history of that, and I think back when we were working on 47 gigahertz, we were experimenting with a little bit larger diameter, larger wavelength opening, which is really a narrower beam width feed to maybe under illuminate or to have less spillover. So I scaled that. I scaled that one back to 24 gigahertz, and this has really been my best performer here. And even with the flare, as ugly as it looks, a friend of mine who is a machinist took a piece of aluminum here and milled it out so it had like a 27-degree angle on the IMU feed. If you look at the IMU feed, in fact, let me just go on here. This is actually a drawing of mine. So to give you some idea what an IMU feed looks like, generally speaking, the opening here, this is almost a wavelength, so you can kind of scale it at other frequencies, and this is almost 2 wavelengths here. This length and diameter and the flare are the most critical items in determining the beam width of this feed for a particular antenna. Less so, but still somewhat important because it affects the angle, is the input diameter. And all I did here was go with what I call 7/16 hobby brass, which is what we have that when you flare it out, it'll fit into a WR42 flange. And so that's what I started with, and a lot of that determines what the angle is going to be depending on the transition length. And this thing has probably been my best performer so far. And I was talking to Paul Wade last night. He's going to take a look at the actual pattern of it so we can see how that affects my dish. But in reality, when you go through the measurements, and I highly suggest Paul Wade's online antenna handbook, and it'll tell you how to take any offset fed dish, which is kind of, it's just a subsection of a larger prime focus dish. But the question is what part of the prime focus dish is really this offset reflector that you have. So in essence, it's probably just a small fraction of it, but he'll help guide you through. You have to find the deepest portion of the dish, and knowing the minimum, width and the height, you can determine the equivalent F to D of it. Theoretically, my dish is about 0.7. So theoretically, one of these smaller feeds, actually this one here is a little bit smaller in diameter. This uses a standard copper fitting, should work better than this guy. But in reality, I guess I'm under-illuminating my dish a little bit, maybe because the edges are not as perfect as they should be. And if I were illuminating the whole dish, then I'd get a lot of I guess we'll call it negative influence on the pattern. So, we try what works for us, and even though theory may say one thing, if something else works, go for it. And that's kind of been my philosophy. All righty. On transverters, I typically try to do everything homebrew or with surplus. So these modules here by the DMC Corporation have been quite helpful over the years. This is a nice PLL, and I used one of these originally. It's phase locked, but the reference is not as stiff as a 10 meg GPS source, so it does wander somewhat. Down converter, this isn't really too great of a performer, but the up converter here and this power amp, and of course power, kind of a misnomer, power is 50 milliwatts, but it's a good TWT driver. And even the output section here is about a 50 milliwatt amplifier also. And this little up converter, it was designed for 310 IF in, and then I guess 2200 out or so, and give you 23,000 out. That is still a usable a component, and then you can use like Pyro Joe. I call them Pyro Joe 24 gig filters. You go on eBay, I think he still sells them for $12.50 US dollar. That's quite a nice little component to help you get on the band, and even two of them, or even one of them will work for a 2 meter IF. I mean, it's got that good a selectivity. So those are some of the components I've used there from DMC, and some of these other ones here. These let's see, who makes those? From the West Coast. Celeritech, and PCOM is what I was thinking of. These guys here, if you see any of these, now they're not designed exactly for 24 gigahertz, but they're close, and their limitation is they like a higher IF. You're not going to use it down at 2 meters or 432. 1296 better. 2 or 3 gig IF, they're super performers. Some of these guys will actually give you an equivalent of about a 2.5 dB single sideband noise figure. Now, there's no filtering built into it, so you might measure a double sideband noise figure of several dB. You put a filter in front of it, gets rid of the image, and then you're left with a single sideband noise figure. But they are several of them available that are sub 3 dB, so they're a nice little building block for getting started, and then you put a nice filter on the front end of it. So, and some other modules, these are doublers. This is a nice little LNA. I call it a Will Jensby LNA because he had supplied them years ago, about a 4 dB noise figure. These particular modules here are just diode front ends with an IF amplifier and give you a nice, 10 or 12 dB noise figure that you can put some gain in front of. So there's several out there that can be useful. All right, and this is my transverter all built up here. I'm using a phase frequency west brick here with an external 99.6 megahertz reference that I pump in from the shack. And that's what the reference is for that. Here you can see the Pyro Joe type of filter. Here's one of those little PAs, 50 milliwatt. Here's my little indicator to show I've got drive. And this thing has evolved over the years. That's why it kind of looks a little ratty, but it works. It's out there at the feed, or out on the feed support. And here my 50 milliwatts here goes into the TWT, which is behind it here. And here's a shot of one of the tubes. This is a Thomson TH3864. These are 28 gigahertz tubes with WR28, so it's the 26 to 40 waveguide. And even as is, they work very well down at 24 gigahertz. And I've transitioned from WR28 to WR42. And also, what I had to do here is I took a lot of the guts out of this assembly and used some high voltage tape and Pookie. And actually, I've got about 100-foot extension cord, if you will, of high voltage wire that goes from out at the feed back into the shack. Because the first time we tried to make a Q on 24, I brought this 14 kV supply outside in the August summer weather, and it arced over and trashed out one of the transformers in there. So it was a rough start, and that was even before we made a Q. So from then on, everything is inside the shack. All the high voltage is inside the shack. And the magnets work very well for tuning. You got to make sure that you don't kick out on helix current, but if you have a good supply that limits well there, then you shouldn't hurt the tube. But I've done a lot of tuning with magnets, and they work very well, just trying to optimize it for a particular frequency range and also optimizing the helix voltage. Unfortunately, it seems like the more you put in, the more you get out. But I'm already up at like 12,600 volts, and I'm just trying to minimize any catastrophes from happening, so I just leave well enough alone. But it runs 100 watts as is. All right, and a little bit about software. I use a program by K5GW, Gerald, who spent a lot of time working with me to come up with options of telling me what my offsets are for different frequencies. As a lot of you know, I use multiple feeds. The only feed that's at the focal point of my 5-meter dish is at 10 gigahertz, and everything else is offset. So we have factors in there that calculate effectively where the dish is aiming. So these top As and L's here are for the 5-meter dish. This is for the 2.4 meter offset fed dish. So I've got two sets of absolute encoders coming in, and I can read them all at the same time. So that shows where that dish is aimed. And the significance of this is Gerald's got a nice planner in here where you can just thumb through. You go into the planning mode, and if you want to go out by day, you just keep on hitting the D key. And if you want to go backwards, you turn off the capitalization, you go backwards. It's a great planning tool. And it's also good for looking at mutual Doppler, as I show here. Like this is in a sked I have with F2CT. You can see the mutual polarization is roughly 90 degrees, which is significant because we run vertical in Europe and horizontal in the U.S. And you can see the mutual Doppler, and you can see my self-Doppler up here. It's actually 41 kilohertz at 24 gigahertz, which is quite a bit, but well understood. Another good program that Doug here, our host, has made available for us is his planning program and also his system analysis program. And I just show a typical example here of this is the program at 24 gigahertz using this particular feed, which I think is 2 wavelength by 3.1 wavelength length, W5LUA feed. It's an optimized feed. And you can go in here and you can put in different diameters, different feed types, and over here it'll tell you your signal to noise. No, it'll tell you your sun noise and moon noise. It's hard to read at an angle, but sun noise and moon noise, and also with your power in there and other station information. It gives you some idea of how strong your echoes would be and how strong the other stations would be. So this is quite a good tool. And I must admit, Doug, when I went on 78 gigahertz with my 1-meter dish, that thing was spot on, as they say. So it worked very well up at 78, or compared very well. Now, something else that I found of interest, and I had to kind of be reminded of it by Gerald, so I went back to my old radio astronomy book, was the actual moon temperature. At lower frequencies, it's fairly constant. In fact, even at 3 centimeters, it's roughly 200, 210 Kelvin. And you can see as you go up in frequency, like 1¼ centimeters, which is 24, there is a difference between first quarter, full moon, and actually there's about a 3.5 day lag as to when from full moon to brightest in terms of temperature. So we see some difference in moon noise depending on the cycle of the moon. And this degree difference here depends on how low a noise your system is. If you have a very high noise system, then that will tend to mask this. But if you have a real low noise system, of course, obviously you're going to see more moon noise, but you're also going to see a bigger variation between, say, first quarter and full moon. All right, some of the real challenges here. Doppler, for one, spatial offset, which is, that's probably an easier one to contend with, and then atmospheric absorption, and then my last comment here is where is perigee, because we are, where is perigee in the moon cycle and the importance of that. All righty, the Doppler effect. You know, this is the change in frequency, I'll just read it here, of a signal that occurs as a result of the source and the observer moving relative to each other. And of course, we hear that when the train is sounding its horn. As it's coming in, it's a little bit higher, and as it's going away, it's lower. Well, it's the same thing with the moon relative to the Earth. And it does scale with frequency. Down at 2 meters, you might have 300 hertz Doppler at moon rise. Well, you can just take 24,048 divided by 144 times 300 hertz, and you'll probably get a number that's close to 100 kilohertz. But it's known, and if we're GPS locked, you know where to look for somebody. But it does scale up in frequency. All right, since the angular velocity of the Earth is faster than the moon, it causes the Doppler to be a maximum at moonrise and moonset and a minimum at zenith. So it'll always be higher in frequency as the moon rises, go to 0 at zenith, and then it'll be negative by a similar amount as the moon sets. And also there is a slight hook effect on the end, and I can't tell you that from having listened to echoes, but I can tell you that as having listened to the lunar orbiter as it went around the moon, it was really kind of cool because as the lunar orbiter flipped around the moon, it was like on around, I can't remember what frequency it was on 2 gigahertz, but in that frequency range, as that thing started to disappear, you hear a little bit of a hook. And it really had a funny sound to the Doppler as it just kind of disappeared. Well, the same thing happens kind of here as the moon tends to tuck around the Earth as it's setting or is coming around the Earth as it is rising. But normally that doesn't affect us because we're hardly listening to echoes, at least on the microwave bands, right at the horizon. All righty. I put up the F1EHN program because I know a lot of you use that. It covers some important things like this here is for me, and you can see on 1296 shows my Doppler at my place. I also use Willie as an example here because Willie, for me the moon is rising. For Willie, the moon is almost at zenith, so it's almost straight up for him, and you can see his Doppler is only 400 and some odd hertz. Now, this is at 1296. But you also see mutual Doppler is 1.76 kilohertz. And we'll talk a little bit about that here in the next couple of slides. And what I'm kind of getting into here, I've got a couple of slides on random operation on CW and also on scheduling. Because on random, it's pretty easy. You know, when you hear a station calling CQ, depending on what frequency you're on, you hopefully have that inputted in your program. Even Joe Taylor's program has that. You can punch in, you know, say 1296, and if you hear LX1DB calling CQ, and I'll say if I hear him, because it'll be a bigger difference for me, I just figure out what my self-Doppler is, and basically I plant my echoes on his frequency. And, you know, for him, his Doppler may be quite small. For me, it might be quite high. But whatever my self-Doppler is, I'm just going to net my transmit signal such that my echoes will be on his frequency. And he will hear me on his frequency. And it may not indicate the same thing on your radio as it would his, but your signal will be on his echoes. And even if you can't hear your echoes, if you could, you would know what the offset is. So if it says, well, my echoes will be plus 3 kilohertz, and so what I would do is if I heard the other station calling CQ on 1296.010, I would put my transmitter on 007, And I may not be able to hear my echoes, but he will hear me on his frequency. So that's random operation. You just always use self-Doppler correction, and you'll know where to put your transmit signal such that he will hear your echoes. And now the problem that you kind of get into a little bit, and I've kind of seen a little bit, and it happens a little bit even on digital, and most people that are on digital say that they will be on a particular frequency and you tune for them. But a lot of the cases, even on CW, if somebody spots the fact that, well, I hear a certain station on a certain frequency, that's only pertinent for you in that area, if you will. But for us over spread out a continent, it's quite a bit different. So there will be differences in frequencies that are as a result of mutual Doppler. There won't be any frequency error because we all know our frequencies pretty well, but most of the difference will be in the fact that there is this mutual Doppler that we need to contend with, and it's most obvious on a schedule, and we'll talk about that here. If we look at this is a comparison of 1296 and 24048, you get some idea of the difference in the Doppler. And here for 1296, the self-Doppler for me is plus 56 kilohertz, and for Willie, it's 8 kilohertz. So this is at 24048. So if his echoes are on 24048 and 8.4 kilohertz above that frequency, mine will be on 56.9 kilohertz. Where is it? Oh, I'm sorry, it should be over here. Mine will be on 56 kilohertz, and Willie's will be on 8 kilohertz, and the mutual Doppler will be 32 kilohertz, which is actually the geometric mean. We'll kind of go through a calculation of that here in the next slide. So my echoes will actually be on 156. Willie's will be on 105 on his dial, and if we were tuning for each other would be on the mutual Doppler frequency, which is the 32.7 kilohertz, which is nothing more than the geometric mean between the two Dopplers. So you take the 8 kilohertz and the 32 kilohertz, you add them up and divide by 2, and that gives you the mutual Doppler. So it's actually kind of a frequency in between, if you will, between both the self-Doppler frequencies. So if Willie and I are running a schedule, and these are the self-Dopplers, then I will hear him on 10368 132, and he will. I will hear him on 10368 132, and he will hear me on that same frequency. So that's typically what we try to do when we're running schedules, especially on the higher frequencies, is to just set your transmit frequency for the exact frequency and then tune for the mutual Doppler. It'd be difficult for somebody over here in Europe to say, well, I'm putting my echoes on 100. Well, they're not going to be on 100 over in North America, guaranteed. We can go back and reverse calculate it, but the way things are set up in the program, that would take a little bit of some quick math while you're trying to figure out where to put your signal. But the most important thing to remember is when running a schedule is just to put your frequency on the transmit frequency and tune for the mutual Doppler. All right, let's see. I said that there. The spatial offset. Basically, there's about a 90-degree spatial offset between North America and Europe. And there's some obvious different offsets between, say, Europe and Asia. And what that means is, or why that's a concern, is that we use linear polarity on 24 gigahertz and higher. I'm still on linear on 10, but a lot of people have migrated over to CP, which minimizes that effect. You don't have to worry about it. But on 24 gigahertz, we're typically horizontal in North America, and it's vertical here. And you can see that in some of these programs. Let me just show the program I use here. This shows the mutual polarity, minus 93 degrees. So between me and Guy, at this particular time, we have about a spatial offset of about 90 degrees. So it works out pretty well with North America being horizontal and Europe being vertical. And of course, if you're 45 degrees out, you get about a 3 dB decrease, if you will, in signal strength. So you got a big window in there, but when the dBs are hard to come by, you like to be as close as possible. Let's go back here. And the other thing, atmospheric absorption. This is kind of what we face also at low elevations. Doug's recent addition to his library of software is this atmospheric absorption program. I haven't spent a lot of time with it yet. I just used the defaults that were in Doug's program, but the important thing is, with the problem we have at 24 gigahertz is the moisture absorption. We have oxygen absorption problems at 47, but really moisture absorption problems at 24. And this just shows as an example, and you can go play with this easily. This is with two stations aimed at 45 degrees. We show a combined atmospheric loss of a dB, which is like a half a dB at each station, which is not too bad. I mean, it's reasonable, and you hate to throw away dBs, but even at 45 degrees, you're still cutting through a lot of atmosphere and getting to the moon. When it really gets worse is when one of the stations is lower. And down at 20 degrees, you can see we lost another dB or so. And with this number right here, and if you go down even further, when one station's at 20 degrees and the other one's at 5, we're down about 5.5 dB. And the reason I bring that up is because right now perigee occurs at southerly decks, so there's not a lot of common window between us and Europe. So the question is, where is perigee? And this is an interesting thought here, because there is a 2 dB difference between apogee and perigee. You can see that when you go through the calculations. And if you look at it, back in 2002, when was it? The first time I heard my echoes on 24 gigahertz, which I think was in 2000, the moon was up at near zenith, and it was perigee. Boy, how nice would that be? And then it started to get lower and lower, and in 2008 was the next time that perigee occurred at northern deck. And, of course, you probably enjoy the fact that it's reversed right now, but the way I look at it, and looking at the planner, it'd be 2017, Guy, if we can wait that long, for perigee to occur at northern deck. And I got to tell you, I'm looking forward to that, because I've been trying to work Guy and a couple other guys on 24, and it's been tough, because you have a very limited moon window, and the lower it is, the more the atmosphere affects it. So, I mean, that's one of the things that draws me and other guys to this band anyway. So we got a little bit of time to wait. And just kind of a quick summary, since I think the paper said above, and I think I've still got a few minutes, right? Just to give you an update on 47 gigahertz, the first contacts were made back in 2005 by Sergey, who had a dynamic 150 watt, 180 watt TWT, and we could hear him on, very well on CW. Gary 86 FP, myself, and where the heck is Barry? Whoops, Barry. Wow, I forgot to put Barry in there. Barry should be in there also. Oh, shame on me. Good thing he's not here. Doggone it. I just saw that. Anyway, that was when the first QSOs were made. And I heard some noise since then about a fellow out in California, kind of a younger guy, KF6. He was building his own 30-watt transverter. And I was thinking that maybe he might be getting on the moon. He probably will, with some coaching from Gary 86 FP. But there's really been no activity since then. If anybody is interested in 47 gigahertz, I ran 30 watts. That's probably about the minimum acceptable to try to do any good. But I think if you want to get on that, or if you have some equipment to get on that band and you let it be known, people will get on. It's just a matter of changing the feed out and going back at it. But there's been no activity since then. And on 78 gigahertz, we're kind of stalled out there on transmit power. I used a little 1-meter dish, of all things, and set it in the middle of my 2.4-meter dish, and I got 7 or 8 dB of sun noise. And Tom Williams had built up an LNA that actually has a lower noise figure than what we used on 47 gigahertz. But we're stalled out on power there right now. And, that's kind of it on frequency. All righty. How much time do we have? 5 minutes? Okay. Let me just go on and show you some other stations here. This is Sergey's RW3BP, who's really, I have to say, like the father of millimeter wave and microwave EME. A very nice 2.4 meter metal offset fed dish with the feed system, of course, out here. And here is Willie LX1DB. He's got a 3 meter dish with a 42 watt PA, and I've had a sideband queue with him, and he does very, very well. And this is Brian G4NNS's, which I guess we'll probably see early next week, or some of us will, with a sub-reflector, feed on 24. And here's Johannes DF10I, who also has a sub-reflector right here. And he's got his TWT and everything else hanging on the support. And this is OZ1FF, probably the lowest power station, 1.8 meter dish. And he has worked LX1DB and OK1KIR, I believe. So he's one of the guys that I've been trying to work besides the guy here, F2CT. So let me just kind of go back to the summary here a little bit. There aren't a lot of stations on that band, but I got to tell you, most of the fun is just making the queues. We do hang out on the HB9Q logger, and that's probably the best place to just kind of check in, put your call, in there, and watch the traffic, because there's a lot of traffic on the 2304 and above part of it. That's a lot of the microwavers that you're going to see out here. And it's also very useful for 1296, but I predominantly hang out on the 2304. But that's HB9Q. And it's mainly just technical chat and scheduling and stuff like that. We try not to handle any QSO information, as you will, because that's kind of the taboo thing that we know about. But it's really a good place to interact. And the latest slides, I know they might do something here with the latest slides, but I'm going to put them on our NTMS reflector when I get home, and so you can pick them up there, because there's the dimensions of the feed horn will be on the latest slides. So I guess that's kind of it. That kind of, where we are on 24 gigahertz and not too much going on above it, but kind of ready when somebody else is.
Thank you very much, Al.